like
sort
one,
of
but
touched on
honestly,
it
that
and
the
actually
entire movie is like one scene in Infinity War.
Okay, so I've started recording and we have 30 seconds of us talking about Marvel. That's awesome. Let's talk about combining spectroscopic techniques. So in terms of what we can do with the mass spectra we get, we can look for a few things. We know some rules about it. We know how it works. We know that the heights of the peaks tell us how abundant certain fragments are, right? So the more stable the fragment is, the taller the peak will be on the table because, or on the spectrum, because there's more of it.
Does
There's
this go
more
for all
abundance.
of them or just mass?
Just for mass, yeah.
Okay.
A peak can be made of different types of fragments as long as they all have the same mass to charge ratio, because you can maybe create a few different fragments that all add up to the same mass and they'll all fit that same position on your spectrum. They'll all have the same mass, so they'll all combine to form one large abundance peak. And this is new stuff. Here's some bonus really cool stuff. Isotopes have different masses. Who would have thought? You know, if you chuck some extra neutrons on something to make an isotope, it's actually heavier. We know that. A fragment can have 2 or more peaks of differing heights if it contains certain elements where it has an isotope that exists in a certain abundance where it'll actually produce a noticeable peak on your spectrum. For instance, we know most carbon atoms are C12, but about 1% is C13. So not only will you have your molecular ion on most spectra, but 1 unit heavier, there's often a very tiny blip to the right of the mass of the molecular ion peak, right? You know, the parent peak, the one that tells you how heavy the molecule is. There's often a tiny one, 1 unit further along the scale, because 1% of all carbon atoms are C13. So a small, so if you look at any of those molecules, chances are they might have maybe 1 C13 in them. Some molecules won't, but overall there'll be some molecules that will produce a C13 peak, so a mass 1 unit higher. Now, chlorine's interesting. So chlorine exists in 2 really abundant isotopes of 35 and 37. And so chlorine 35, there's about 75% of chlorine atoms in that state, and 25% exist as chlorine 37. So we're going to see a peak ratio of 3 to 1, because 3/4 is 35, 1/4 is 37. So you'll see a 3 to 1 ratio, and they're going to be 2 units apart. So on your scale, 35, 36, 37, I'm just drawing here on the whiteboard. So you'll see a ratio of like this, 3 to 1, where the heights are at a ratio of 3 to 1. And so this will be an indication that you have chlorine in your molecule. So remember that rule, because we're going to do some tests in a couple minutes where I'm going to throw some spectra on the screen, and you're going to tell me, based on the ratios of peak heights and stuff, if any of these atoms are present in the compounds. Now, bromine's the 3rd type of isotope we're going to look at. So we have carbon, chlorine, and bromine. And bromine's isotopes exist in roughly a 1-to-1 ratio, 50% of each. So the peak heights should be the same, roughly the same height. Cool. And the other thing to notice is that bromine is super freaking heavy, 7981, okay? You're only really going to have bromine if you notice your molecular ion peak is around like 150 or 200. You know, it's going to be a really heavy molecule, plus it's got bromine. So that adds up to a lot of mass. So if your molecular ion's around 60, there's no way you can have a bromine, so don't even bother. Just use some kind of common sense looking at that stuff. Cool. So those 3 isotopes are what we're going to look out for in some of the following spectra. Now we know what a spectrum looks like. We know how to label some of the key peaks, like the molecular ion peak. And if you see, look closely, there is a tiny blip to the right there. You all see that little blip to the right of the molecular ion peak?
How do you tell this molecular ion? I missed that.
Just, it's the largest significant peak to the right.
Okay.
Yeah. So that little blip tells us, oh, that's the small percentage of molecules that contain C13 atoms in them that cause that 1 unit extra mass. Cool. We know, yep, so there it is labeled. We have a base peak. The base peak is just whatever the highest peak is. And just like with the molecular ion peak, to the right of the base peak, you also might find a tiny blip there as well of some of the fragments that make up the base peak having that extra C13 in them. So some of you were asking about what those little blips were last time. Now we're spending more time looking at those little things. And the other one to watch out for is this little blip to the left of some of these significant ones. And that's due to the loss of a hydrogen. So if you have an OH group, often an H is lost from that, right? So if you just, or a carboxylic acid maybe, or something like that, where you can remove a single hydrogen, that'll cause a little blip 1 unit down. Cool. So to summarize what we can find out from a mass spectrum, the first one is the molecular mass of your compound. You look at the molecular ion peak and it tells you that. We can look at certain elements. We can figure out if certain elements are present, like chlorine or bromine, based on the ratios of peaks. We can find out if nitrogens are present, because most of the time you'll find that your molecular ion peak is odd. I did mention this briefly last class, but if you have nitrogen, you're going to have some even mass peaks in your spectrum. And we talked about what makes a fragment particularly stable. So something that's a tertiary carbocation is particularly stable because that carbon's positive charge is stabilized by all of the bonds around it, which can contribute electrons to stabilize that positive charge. So tertiary carbocations are more likely to exist than something like a primary one. So what we learned just in the past few minutes that's new is that we can actually figure out what atoms are present based on a mass spectrum. So IR is good at telling us some of that stuff. NMR can indicate whether some of those atoms are bonded to a carbon, because the carbons will be more or less de-shielded by those atoms. But this can also really confirm, just double check our confirmation, that we have some of these atoms present based on the ratios of isotopes, which is really neat. Cool. Cool. So here's one. We have this compound here, so we're told what it is. Good old amine. So we have an isotopic peak 1 unit higher, just due to some carbons. There's an even fragment at 70. That tells me that's a fragment that contains nitrogen, causing that even mass. And even one at 30 as well. So the total mass, 87. This one's a haloalkane. This one contains chlorine. These are just some examples before we get to the quiz questions where they don't tell you in the title what to expect. So we have an M+ ion up there. Because it contains chlorine, remember, some will be chlorine 35, some will be chlorine 37. So 2 units higher than this really tiny molecular ion peak, there's an even tinier blip. So that's some of the molecules that contain the 37 chlorine isotope. It's a 3-to-1 ratio. So those peak heights, even though they're tiny, they're roughly, their heights are 3-to-1. So
if the peaks are that tiny, what happens if the printing goes haywire and doesn't show us that? I'm worried that it'll be faded or something.
I double check them. I try to do them myself and make sure it all makes sense. And cool. Even further down, fragments that contain chlorines. Even the fragments can have a peak 2 units higher, right? That contain the chlorine 37 isotope. So if any of the fragments contain chlorine, they should produce a peak 2 units higher. That's third as high as the peak you're interested in, because they contain that heavier isotope. And bromine. What's the ratio of bromine isotopes? 79 and 81. What's the ratio?
Approximately 1-to-1.
Yeah. And look what we see there. Look at the molecular ion peak. That's the one that contains bromine 79, and then we got bromine 81. Same height. That's a nice little picture there. Cool. 2 units higher, 1-to-1 ratio. Cool. Even the fragments, so this tells us this fragment must contain bromine because it's producing a peak 2 units higher. So that's awesome. And there's a little blip in between them. What do you think causes that? You see the little blip between these two bromine isotope fragment peaks?
Heavier carbon?
Yeah, just heavier carbon, C13, right? So this little blip's just caused by a bromine 79 fragment having a C13 carbon. That's cool. Isotopes, man. Okay, this is an alcohol example, or anything containing an OH. So it could be, carboxylic acid.
No, it's not. Never mind.
This is just a regular old alcohol. So we got a tiny blip, m plus 1, so you know the mass of the molecular ion plus 1 unit because it has C13. M minus 1 due to the loss of a hydrogen from the OH group. Okay, now here's where we practice. What do we notice? Molecular ion peak. What mass to charge ratio would we say it's located at? Yeah. 87, yeah, 87, because here's 88, 89, 90. Yeah, so 87. And there's a little blip to the right. What causes that? Somebody else? Just double checking. Little blip to the right here, the molecular ion peak. Yeah.
That's just the heavier carbon.
Yeah, C13 carbon isotope. Cool.
How do we know that that's the molecular peak?
It's the most significant peak to the right on the axis. Yeah. Like this little tiny one, you might be thinking, oh, how do I know that's not the molecular ion peak? Normally it's more significant than that. I can specify to you, I'll make sure it's an obvious case, and the blip really is a little blip and not just a really confusing molecular ion peak, because that wouldn't be very fun or fair. Now what about to the left? There's a not insignificant peak here to the left. Yeah.
Loss of hydrogen.
Yeah. So that tells me it's probably some sort of OH thing, maybe. Any signs of maybe other isotopes that aren't carbon isotopes? So any bromine or chlorine signs? No?
I'm not sure. What was the thing for looking for nitrogen? There were rules.
You'll have even numbered fragments.
Well, we do have that. 30.
We do.
42, 44.
So maybe it's not a loss of a hydrogen from an OH group. Maybe we're just losing random hydrogens.
So when we say even numbered fragments, we mean fragments that fall literally on even numbers.
Yep, and that's what you observed. At 30 and 58, you pointed those two out. We have really significant fragments that are even numbered, so it must contain a nitrogen. So good observation there. And the H must be the loss from the amine, I would guess. That's a hydrogen you can lose.
And these are rules that we do have to remember.
Yeah.
Okay.
Yeah. Now this one, okay. Ooh, pretty obvious right away, I think.
Yeah.
What do we see? What's significant?
Molecular ions.
Your bromine prism.
How do you know?
Because the two on the far right are even.
Their heights are in equal abundance.
Do they have to be like that on the far right, or can they be anywhere?
The molecular ion peak, if the molecule contains bromine, will form a peak 2 units further along because it contains an equal percentage of that isotope that's heavier, right?
But it has to be 2 units along from the molecular ion peak.
Yep, and any fragments that contain the bromine as well. But bromine's heavy, and all of these fragments are down here around 40 units, right? Bromine weighs twice as much, so I would say none of these fragments can possibly contain bromine. So these are all non-bromine containing fragments. Cool. Now what I see up here though are little blips, and they look to be about the same height. If you look closely, there's 2 groups of 2 blips here. So those would be bromine containing fragments because they are 2 units apart as well. See? Awesome. So 122 would be the molecular ion peak. So if you saw these two together, make sure that you recognize this peak at 124 does contain the heavier isotope, but the true molecular mass is around 122. Cool. Now what about this one?
Well, it has nitrogen. There's lots of even numbered ones.
I'm seeing a lot of, yeah, like this one at 58, but
So they have to be big peaks.
you have to have a few really stable peaks. That tells you.
So that means it can only be nitrogen if there's a few with.
Yeah, you have 2 or 3 really significant peaks and nothing else at really odd numbers. Like there's a significant peak here at 29 and 27. That makes me think maybe it's not nitrogen containing.
It's not because the molecular ion peak is even.
And that's the other clue, right? It's even.
The molecular ion peak was the first one to the right of the base peak. The first significant. And the base one's all over there.
The molecular ion peak is the mass of the molecule, and you form this ion simply by ejecting 1 electron, but not breaking any bonds to remove any atoms from the molecule. So it has the same mass as the molecule itself. This ion is just ionized by the removal of a single electron.
So it's the furthest to the right.
Furthest to the right. Yeah, that's a
Absolutely.
molecular ion peak.
Okay.
It's a
sorry.
molecule in ion form. The base peak is just whatever peak happens to be the tallest. So this would be the base peak here. So we have a lot of, you notice the molecular ion peak is an even number. We still have a good mix of even and odd fragments. So I wouldn't say, there we go, nitrogen. But we have something that just is usual, is just a good mix of, fragments, but nothing really significant. No bromine or chlorine isotopes. Doesn't look like nitrogen's there. Cool. And it's kind of hard to tell whether there's an oxygen there. You couldn't get that info from here. Like, there's no way to guess that. Okay, what about this one? Ooh, I see a couple examples that tell us what's in there. Yeah.
So, 2 up from your molecular ion peak, you have one that's about a third of the size, so it's going to contain chlorine.
Good. So you're looking around 78 and 80. But I also see the same thing happening in a fragment at 63 and 65. Yeah. So this fragment contains chlorine. Not all the fragments, like these ones down here, don't have that ratio. And chlorine is kind of heavy itself, so they can't be in there. But really good. Those are easy to spot. Awesome. All cool with that. Nice. This is the second last one, I believe. The base peak, the tallest one, looks like it's around 57. The molecular ion peak, well, there's a few blips on the end there, right? At 85, 86, and a very tiny one at 87. I would
There's
say,
bromine.
when I see 3 in a row, I think something. I think the one in the middle would be the molecular ion peak. What would cause the peak above it? And the peak below it?
Lots of hydrogen.
Yeah. Cool. Yeah. If it contains an OH group, like an alcohol or a carboxylic acid, those H's are normally given away. So M-1 because it lost a hydrogen, and there's a little blip above it caused by the C13. Sweet. All right, so that was it. Here's our first practice problem. All 3 spectra are here. We're going to run through it before you actually study some yourselves and work through it. So rough observations. Just whatever you see on any of these 3 spectra, let's talk about it. What do we observe? Give me something.
There's an OH group.
Cool. Broad, strong peak on the IR spectrum. So OH, yeah.
Also, left of your one down from your molecular ion peak, you have a little bit.
A little bit down here.
Loss of hydrogen.
Loss of hydrogen. Yeah, and I'm squinting and I see one above as well. So C13, there's a little blip there. But yeah, what you said is most important for like confirming, we feel pretty confident there is definitely an OH group. So some sort of OH group. Any other information from the IR about like what could it be?
You've got CH and you've got, there's nothing at 1700, so probably not C double bonded O. But you've definitely got CH.
So we're saying no carbonyl group. So
yeah.
that reduces our options in terms of what functional group could exist in our molecule. So
But you have got one at 1000.
around 1100 or so.
Yeah.
What
That's a 1000.
peak? What bond causes that peak there on the IR spectrum? Around 1100. Yeah.
CO.
Yeah, C single bond O, which makes sense because this OH group needs to be bonded to a carbon, right? So it's just that one, right? So that's just something reassuring to see. It's not just a random OH group floating around. Okay, and that's about it. The fingerprint region's kind of funky here.
So
I don't
how do
believe
you
that's anything.
know how it's arranged if it's a big one?
We're gonna figure that out based on carbon environments and the
Oh, yeah.
molecular mass. So how many carbon environments have we got?
3.
3. Okay, so 3 C environments, and what's now Ben, I don't know if you can see from there, but you gave us a clue about the molecular ion. What would you say it's at?
74?
Yeah, right, looks 74. That even mass, helps confirm some things. So our compound weighs 74. It must have at least 3 carbons, so it's maybe C3 something, H something, O, right? Okay, O weighs 16, yeah? So if we take the mass of 16 off our total mass of 74, what are we left with?
58.
58, okay. Now, what do 3 carbons weigh?
36.
Right, so 58 minus 36 is what?
22.
Do you think it's possible it's the formula C3H22O?
Probably not.
Maybe not.
Well, we know that
Unless carbons are allowed to accept 10 hydrogens each or something. No. So
Expanded octet carbons, a groundbreaking theory.
yeah, expanded octet carbons. New chemistry, guys.
talked about this morning.
So this
It's gonna
is
be
this
expanded quartet.
C3H22O is an option, but it's not a great option. What else can we do to maybe create a more reasonable empirical formula? Yeah.
Throw more carbons at it.
Can we do that? There's only supposed to be 3 carbon environments.
Make it
Doesn't make it
symmetrical.
symmetrical.
So
Yeah,
have your
doesn't
OH in
make
the
the-
middle bit and then build out.
Good. So we have multiple
5.
carbons, but some are in the same environment,
Yeah.
right? So what if it was C4H something with 1 O?
Wouldn't be symmetrical.
So that would be, because instead of having 22 hydrogens, we'd have 22 minus 12 since we added the mass of 1 more carbon, right? So that's 10. So C4H10O does sound a lot more reasonable to me. Yeah?
Yes.
And really it would be C4H9OH because we know one of the H's is tagged to the oxygen to make that alcohol group. All right.
Would you be wrong if you said C4H10O?
No, that would be fine.
Okay.
Yeah. At some point, you do need to name and draw the structure on your report, though. So initially, you could
You'd
say,
figure it out.
I think the
eventually.
formula is this, and then you would go on to draw the actual structure. Okay. Now, do we want to take a break and try to draw what we think this molecule looks like, based on the fact that there are 4 carbons, but 2 of those carbons must exist in the same environment?
Do you have a mass spectra sheet, like the green sheets?
Yeah, I do somewhere. Here we go.
Because I'll go looking for it and be like, why don't I have that?
That's right.
There you go.
Thank you.
Spaditas.
Yeah, got it.
I don't need scrap paper. So we do it here and then look at this and go, but what was I confused about?
Figure it out.
Either that or like a whiteboard.
That's coming up.
That's true.
A little whiteboard. If this table was a whiteboard, that'd be so bad.
It would be. Oh.
Math group, I'm saying.
You can
Yeah.
get like sheets of whiteboard that you could stick to the table.
We should really do that.
Like, you know how you can get book covers? I'm pretty sure you can get whiteboard. Yeah.
So, hands up if you think you figured it out.
Yeah.
3 hands, 4 hands, 5 hands, 6. Okay. So, anyone want to share the name of the compound? I know you've drawn it out, but can you think of the name and share that? Ben,
2-methylpropan-1-ol.
sounds good to me.
What do you mean to
Jumping right through it.
Pretty confidently, so.
That's not one.
We know all that stuff. We came up with the formula, so all the stuff I hadn't shown on the screen, we just talked through it and observed. C4H10O, you could draw all the isomers, but really right away, you know you need to draw a backbone carbon structure that has 2 carbons in the same environment, right? So you can draw a few isomers that have 4, but only one of those isomers will have 3. There you go. So we came up with the name, you said 2-methylpropan-1-ol.
That's what I said.
That's perfect. Sounds good to me. Perfect. I'm going to stop there. We don't need to do another example, but what we're going to do is distribute some spectra like this and just work either on your own or in small groups to figure out the compounds yourselves.